now that we've completed our discussion of how DNA goes from DNA to RNA via transcription, RNA to protein via translation, and now that we've talked about how the genetic code is read, we want to spend some time talking about how we as humans utilize that knowledge in combination with technology that we have developed to accomplish some really quite amazing things. Now, I will point out that some of these things are controversial, and my goal for this class, the goal of your text as well, is to impart to you a knowledge of what's actually going on with these organisms. We're going to talk, for instance, right now about how genetically modified organisms are made. Genetically modified organisms are somewhat controversial. There are protests periodically to try to bring attention to the fact that people don't like genetically modified organisms. In fact, it's interesting if you look at the history, very recent history of Europe and the United States. This may be surprising to you, but Europe has been very hesitant to accept genetically modified organisms, and has been much more hesitant than the United States. Much of what we consume, if you go to Kroger and buy food, much of that is going to contain components of genetically modified organisms. Since, as I pointed out before in our class, over half the corn grown in this country is genetically modified. In Europe, that's not the case. There are much tighter restrictions on genetically modified organisms. So we'll talk a bit more about the controversy, but for now we want to spend some time talking about the science behind genetically modified organisms. And so how do we make a recombinant organism? And so that's what we want to talk about at this point. Now, what we have on the screen then is an example of a product that is produced by genetically modified organisms. RBGH stands for recombinant bovine growth hormone. Growth hormone is a hormone that plays an essential role in growth, as the name would imply. So if as a human you don't have enough growth hormone, then you become what's known as a pituitary dwarf. You do not obtain a height that is much greater than it's between 3 and 4 feet or so, and that's a result of simply a deficiency of the pituitary gland during a crucial period of development. It can be corrected today by giving a child growth hormone, and interestingly, that growth hormone is produced from genetically modified organisms, and it's widely available as a result of that. Now, the bovine growth hormone, as you know, bovine means cow, and so bovine growth hormone is produced from the cow gene, and is produced for cows for purposes that we'll talk about in just a moment here. Now, it is interesting that growth hormone is basically the same, whether you're talking about cows or humans. If humans take bovine growth hormone, they don't grow a tail and horns, or grow to be 1,000 pounds like a cow would weigh, but they do experience increased muscle mass as a result of taking that. And unfortunately, as a result of that, there's a demand on the so-called black market, the illegal market for bovine growth hormone, and periodically it's stolen from big dairies and sold to most likely to weightlifters who take it at great expense as far as their long-term health prospects are concerned. But it does allow them to put on muscle much more effectively in the short term. They're going to live a much shorter period of time, but to them, I suppose it's worth it to be buff in the short term. So back to our discussion here. Restriction enzymes are the first thing that we need to talk about in this process. And so it's a relatively simple process, and a restriction enzyme is this. A restriction enzyme can go in and cut DNA at particular points. Now, remember, what we're going to do here is cut out a particular gene from a cow's DNA. And it takes 23,000 genes to make a human. I don't know exactly how many genes it takes to make a cow. The cow genome is sequenced. That information is available. I imagine it's in the same ballpark, but I need to look that up. I'm not quite sure. But let's say it's 23,000, which would be a reasonable estimate. So out of those 23,000 genes, we've got to cut out one. And how do we do that? Well, we use restriction enzymes, as we'll see in just a moment. We also need to introduce the term plasmid. And so a plasmid, interestingly, is a small circular piece of DNA that's found in bacteria. Bacteria bacterial chromosomes are circular, but in addition to that main circular chromosome, bacteria also have smaller bits of DNA that are referred to as plasmids that exist in their cytoplasm. Plasmids are going to be important in this story. Now, here are our restriction enzymes. Restriction enzymes are amazing tools. Restriction enzymes are collected primarily from bacteria, and they cut DNA at particular points. And so here we have a piece of DNA, and here we have the restriction enzyme that's going to cut the DNA. And when the restriction enzyme cuts the DNA, it leaves these edges that are referred to as sticky ends. And so you can see that the DNA was simply cut. Watch how my cursor is moving. It was cut there, and then we went up here and we cut there. And so this piece of DNA will very easily bind back to this piece of DNA, because adenine binds with thymine, adenine binds with thymine, and then thymine binds with adenine, and thymine binds with adenine. And so that is a sticky end. So it's a really simple concept. Restriction enzymes cut DNA at particular points, and restriction enzymes use these things we call sticky ends. Now, here's a little animation that's going to show us an overview of this process. So what we have so far is a cow cell. This could be any old cell from a cow that's living. It could be an udder cell, it could be a cheek cell, and so forth. So we have gotten the DNA out of this cow cell, and the gene that we want is shown in red at this particular point. So all we need is the DNA. We don't need the cell. The cell goes away. Here's the restriction enzyme. It comes through and it cuts the DNA on either side of this gene, leaving sticky ends. There's one sticky end, and so they're highlighting the sticky ends there. And then the rest of the DNA is also cut up. So we have cut up the DNA, and here's the gene that we want. The next thing we're going to do is interesting. Each piece of DNA has sticky ends, and so we are, I'm getting a little ahead of the video here. We're going to do this. We're going to take a plasmid. These are little rings of bacteria that are found in they're found in bacteria. Little rings of DNA found in bacteria. We're going to cut the plasmids using restriction enzymes. That green thing represented a restriction enzyme. And we're going to take the DNA from the cow and we're going to put it into the plasmid. So remember, we have made a genetically modified organism at this point. We have taken, the yellow represents bacterial DNA, the green represents cow DNA. This is DNA ligase. DNA ligase has to come along and seal those ends. So now those two different types of DNA are sealed together. It's fascinating, isn't it? The blue is cow DNA, the yellow is bacterial DNA, and there's no difference in those types of DNA. This is something that's relatively easy to do. We do this in our lab with fish DNA. We take fish DNA and we put it into the bacterial DNA for a reason that we can talk about in a moment, a similar reason to what we're doing here. So now we have all these different plasmids that have cow DNA inserted into them. Now, one thing we have to realize is that we can't, at this point, we're not sure which plasmid has the gene that we want. We only want this little red gene here. And so we take the plasmids and we put them back into bacteria. Hopefully that makes sense. The plasmids exist in bacteria in a normal scenario. The blue represents the bacterial genome. The plasmid is an extra ring of DNA found inside the bacteria. It's shown a little bit bigger than it really should be here, just so we can see it. But it's very easy to get bacteria to take up plasmids. You simply grow bacteria on a petri dish, you dump the plasmid onto the petri dish, and the bacteria suck up that plasmid. Now the last thing that we need to do is figure out which of these actual bacteria contains the desired gene. And once we have accomplished that, then the fascinating thing is this bacteria is going to make millions of copies of this gene for us. And so if we can figure out, which is not too difficult to do, which bacteria contains the gene that we want, we can put this bacteria into a petri dish, and that bacteria will divide. And as it divides, it makes a copy of its genome and of the plasmid as well. And so overnight, we can have, remember, E. coli, which is typically the bacteria used in this case, can divide once every 15 minutes. And so We put this in a petri dish at, say, 5 o'clock in the afternoon. We come back at 8 o'clock the next morning, and we have millions of copies of the gene that we want. Let's review this process once more. Remember, what we're going to look at here is exactly what happened in this video. So here we have the Holstein cow. A Holstein cow is a cow that's used in the dairy industry. Most likely the milk that you drank this morning was from a Holstein cow. We take the DNA out of the cell from the Holstein cow. We cut out the bovine growth hormone gene. We take a bacteria and we take the plasmid from the bacteria using a restriction enzyme, the same thing we used to cut the cow gene out. We cut the plasmid and we leave our sticky ends there. We take the cow gene and we combine it with the plasmid, so now we have bacterial DNA shown in pink and cow DNA shown in red. We put the plasmid back into the bacteria, and now we can grow the bacteria in a petri dish, as we concluded there with on the video. So why would we want to do this? Well, fascinatingly, once we do this, the bacteria has this cow gene, and the bacteria doesn't know it's a cow gene, so the bacteria makes whatever is specified by that gene. And so bovine growth hormone is made by these bacteria, and it oozes out onto the media, or the agar that this bacteria, on which the bacteria is growing, and the hormone can now be collected very easily, as is being done with this syringe here, and used for many different purposes. And so in this case, the bovine growth hormone is used legally with cows to increase milk production. Bovine growth hormone increases milk production from cows by about 20%. There's some controversy over the safety to humans. USDA and Monsanto argued that this milk is indistinguishable from non-treated milk. So in other words, when we take this milk and we look at all the components, the molecules of the milk, they're all exactly the same from non-treated milk. And so that's what our best science indicates at this point. But activists disagree. Now, I encourage you to look at everything skeptically. And as a scientist, I think a responsible scientist is skeptical. Doesn't believe things just because they're told something, but takes something that they're told and looks to see if it's true or not. At this point, our best science indicates that there's nothing different about this milk. And so I'm very interested in looking at scientific articles and evidence that indicates this is not true. But to date, we don't have any of that evidence. So typically, the arguments that are made, at least against this particular type, this particular aspect of genetically modified organisms, are emotional, not based on science. And of course, I encourage you to look at this yourself. But in my experience, what I have seen to date indicates that while it's easy to say, well, I don't trust this. This has a gene from another organism in it, and so I'm scared of it. But using our best technology, which is really pretty fascinating and pretty amazing, we can't tell a difference. There doesn't seem to be any difference, and of course there's no impact on human health as a result of the fact that there's not a difference. Now, a legitimate argument might be the welfare of cows. Certainly the taking, I mentioned what the taking of growth hormone can do to humans, and so the same things can apply to cows, and so that's certainly a legitimate argument. And it kind of comes down to how you feel about the welfare of cattle. Now, in much of the world we view cattle as certainly something that should be treated humanely in every aspect. But we do consume cattle. Many of us enjoy eating beef from time to time, and so the question of the welfare of cows falls into kind of a different category there, but certainly it is a legitimate argument. There's no question that the giving of this hormone will decrease the long-term health prospects of the cow, but you have to ask the question, how many cows live to a ripe old age? And the answer, whether you're aware of this or not, is that not many do. Cows are typically, they live out a useful lifespan, and then they are, can I say this? They're turned into kind of low quality beef. That's simply the way that it works, in hopefully a very humane manner. And we have many restrictions on that at this point. but that's where that particular issue stands. And so this is a very interesting topic, and they're very it's a somewhat controversial topic, as I've mentioned several times, but let me mention this too. So I mentioned the fact that as a human, if you have a pituitary deficiency, you can avoid pituitary dwarfism by taking growth hormone supplements at this particular point in history. And so before genetically modified organisms were available, the question is, how did you get growth hormone? Let's say that you have a child who needs growth hormone supplements. How did you get growth hormone? There was only one way to get it, and that was to extract the pituitary from a deceased human, from a cadaver, and to take that growth hormone from them and to use it in treatment. And so remember, the pituitary gland is a gland that's the size of a pea, PEA, the vegetable, that's found in the very center of your brain, right kind of between your ears is where your pituitary gland is located, in the middle of your head. And so it doesn't contain much growth hormone, and as you would imagine, the need to extract it from actually a deceased human made those growth hormone treatments incredibly expensive and available to very few people. And so the advent of genetically modified organisms means that, although they're still expensive, the growth hormone treatments are available to many, many more people. I mean, and I'm not talking about illegal use in any way here. I'm talking about humans who have a legitimate need, children in most cases who have a legitimate need for growth hormone treatment because their pituitary is not working. They're not producing enough of it on their own. And so that, I think, from most people, I would view that as a positive for genetically modified organisms in this case. Growth hormone treatment is available to a wide variety of people, at least a wider variety of people in developing countries, to which it would not have been available if it wasn't for these genetically modified organisms. Remember that genetically modified organisms are used for many applications beyond just the production of growth hormone, though. We've talked about several times, we've mentioned genetically modified corn. Much of the corn, over half the corn grown in this country, is BT corn. And BT corn is corn that has been modified to incorporate a insecticide that's produced by bacteria. So it's corn that produces its own insecticide. The purpose of this corn is to reduce the overall need for insecticides. Insecticides, while they are not as toxic as they were at one time, we banned things such as DDT, are still less than desirable. And so if we can minimize the amount of insecticides we're putting into the environment, that's viewed as a good thing. And the insecticides that we as humans are exposed to, even on our food, that's certainly a good thing. So there are many applications for genetically modified organisms, but there's no question that there is controversy regarding GMOs, and it's my hope that our discussion in this chapter gives you a somewhat better understanding of what GMOs are. The question really is, it really is a science question. If we look at these organisms and look at the molecules in them, are the molecules the same as the natural organisms, or are they different? If we can answer that, and we can answer that using science relatively easily today, then we can move ahead with decisions regarding these organisms. And I'll point out once more, as I did previously, GMOs offer a tremendous amount of hope for people in developing countries that don't have enough food at this particular point. We talked about golden rice before, rice that has the additional genes in it that cause it to possess vitamins that normal rice doesn't have, correcting vitamin deficiencies potentially in large areas of Asia. We talked about genetically modified corn that can be grown with less water and in soil that has a higher salt content, which would allow people to grow a food source in parts of the world where there are large tracts of land that are just not usable at all at this particular point. There are downsides to GMOs, I certainly wouldn't deny that, but I encourage you to look at the science behind GMOs as you come to your opinions regarding GMOs. On a lighter note, another GMO that we have is a pomato, and so a pomato is a combination of a tomato and a potato, as you would imagine. And so this is a good use of space because you can grow tomatoes in the upper portion of the plant and the roots of the plant. Tomatoes, of course, have to have roots. Potatoes are part of the roots of a plant, and so you have one plant that produces two different vegetables at the same time, or at least two different foods at the same time. And equally important, we have the rooster potato. And so the rooster potato is a combination of the chicken genes with the potato genes. And so in this case, we have an even better situation where we have our meat and our vegetable grown together in one particular organism. And of course, that's a joke. So the tomato is a real organism that really has been produced. But as you would imagine, combining a potato gene and a chicken gene wouldn't be quite as effective. So those are GMOs, and the basics behind how genetically modified organisms are created.